I'm Sean Carroll, author of The Particle at the End of the Universe. I'm going to read from the beginning of Chapter 8, Through a Broken Mirror, which is about symmetry in physics, and in particular how the Higgs field, the Higgs boson, breaks symmetries in particle physics. In an otherwise empty seminar room at the California Institute of Technology, I was seated on one side of a table and local TV reporter Hal Eisner was seated at the other. In between us was a giant bowl of popcorn. Eisner seized a kernel of popcorn and waved it in front of my nose, asking me, begging, really, to use it to explain the Higgs boson. If there were no Higgs boson, would this popcorn explode? It would explode, wouldn't it? This was September 10th, 2008, the day the first protons circulated around the Large Hadron Collider, the giant particle accelerator that we built at CERN outside Geneva, Switzerland. And the attention of people worldwide was focused on a handful of protons, working up the strength to travel all the way around a 17-mile ring for the first time. Hence, reporters had come to Caltech and other universities in other cities to report on all the excitement. It was early morning Geneva time, but California is 9 hours behind, so it was late the previous night for us. Computer monitors had been set up for everyone to follow along, although the strain on CERN's servers soon broke the internet feed. Pizza was ordered and passed around, helping the assembled scientists settle into a comfort zone. A substantial fraction of the atoms in the body of a typical physicist were once in the form of pizza. Still, the local news folks were very reasonably asking, what's the big deal? We know the LHC is important, but why exactly? The search for the Higgs boson was always one of the first things the physicists would offer. Okay, so why is the Higgs so important? And we would say something about mass, breaking symmetries, and then they would always ask, let's get down to brass tacks. Would the popcorn explode? We're really at an historic moment in the history of particle physics. We're at a point where it takes decades to plan, design, and build a new accelerator that can look into new regimes and energies. And so we don't turn on one of these machines very often. So when the Large Hadron Collider turned on, we were hoping for historic level results. And by the end of 2011, beginning of 2012, it seemed clear that we were going to get one. It looked as if we were beginning to see the first hints of the Higgs boson. So early in 2012, I thought it would be a good idea to sort of capture this moment and use it as an excuse, both to explain some deep ideas in particle physics, but also to talk about the human side of this scientific endeavor. These are real people who are devoting their blood, sweat, and tears to answering these deep questions about the nature of the universe. And when it comes to a search like this, it requires more than just a few lone geniuses or even a few people in their laboratories in their basements. You need thousands of people, you need billions of dollars, you need many, many countries to come together over years of effort. And the human race achieved that. That's why the Large Hadron Collider is such an amazing story. It's a story of dedication and cooperation in the pursuit of a goal which is resolutely impractical. We're not trying to cure disease, we're not trying to build better electronics, we're just trying to understand how the world works. So to me, it's a very, very uplifting story. These are human beings who have really dedicated their lives to answering deep questions, and it's hard to think of a higher pursuit than that. I was lucky enough to be there in Geneva at CERN on the day they made the announcements that we'd finally discovered the Higgs boson. In fact, because I was writing a book rather than actually working on the experiment, I was not in the room with the scientists hearing the lectures. I was in the room with the journalists who were covering the story. And the journalists did something that journalists are not supposed to do. They broke into applause. Robert Wilson was a physicist who helped build Fermilab, the giant particle accelerator complex here in the United States. And he was testifying once before Congress back in the late 60s when they were just deciding whether to do it or not. And the congressman wanted him to explain how Fermilab would help tangible things like national defense. And after hemming and hawing a little bit, Wilson said, look, the only way it helps national defense is by helping make the country worth defending. Well, I think it's a great honor to me to be on the short list for the Winton Prize, especially because I think that England and Great Britain, have a real tradition of engagement between science and the public, which I wish that the United States, where I am, would catch up to. We aspire to be that good. And I think that taking science and explaining it to a broader public is absolutely crucial in every aspect of science, but especially so in the esoteric realms of cosmology and particle physics that I work in. And that's precisely because it leads to no tangible benefit. If you're doing cancer research or epidemiology or something like that, nanotechnology, even if people don't understand it, they can still benefit from it in some way. But what I do, and what the physicists who I'm talking about in this book do, all we do are answer deep questions. So if we don't tell people the answers that we found, there's no point in doing it at all. So I think it's an absolutely crucial part of particle physics research that we tell people what we found. And the idea that I'm on the short list for the Winton Prize means that maybe I'm doing it a little bit well, and I'm going to try to do it even better next time.